All right, so here we go with using initial rates to determine the rate law. As we've seen so far, most reactions, rate laws, take on this general form. The word rate is equal to K, a rate constant, the reactant's concentration to some power, the reactant's concentration to some power, and then if there's more reactants, then they'll be raised to different powers as well. And so therefore, the task of determining the rate law, determining what this expression or what this equation is, becomes one of solving for exponents. What is m? What is n? What is any other ones that we have? All right? So here is sample exercise 14.6, and we're going to go through finding this rate expression or this rate law. And I'm going to move this, and I'm going to put this over here, and I'm going to let you write down the entire problem. And then I'll start to talk about it just a little bit. But I'm going to zoom in on it right here. And it's sample exercise 14.6 from your textbook. And it says, using experimental data, determine the rate law. Find K with its units. Find the reaction rate if A and B are these concentrations. And then here's the experimental data for A and B. And the one thing that I probably didn't write down, but I probably assumed, is that you know that this is a reaction. A plus B goes to some kind of products right here, the same example reaction that we've used the whole time. So I'll be quiet for just a second, and I'll just let you write down A, B, C right here, and then all of this experimental data for 3 different experiments. Concentration, concentration, rate. All right, if you need to pause the video just a little bit more so then you can finish writing down the experiments right here, and each one of these pieces of molarities, and then each one of these rate pieces, you can go ahead and do that right now. All right, then we're going to move this over here, and then I'm going to give you some general rules to solve for this. All right. First general rule is that once you're given a bunch of data like this, if something has exponents, like the concentrations or the initial rates have exponents, if there are ones that have all the same exponents, ignore those exponents. So ignore that times 10 to the negative 5th part right here, and then just look at these numbers, because these will tell you relatively how they change. This one's 4, this one's 4, this one's 16. Oh, that quadruples. Maybe you can see some relationships like that, rather than being all messy with the times 10 to the negative 5ths. The second thing is that you want to compare 2 experiments with one similar concentration. So for example, we'll compare experiment 1 to experiment 2, and you'll notice A is the same from 1 to 2, but B doubles. So since A is not changing, that's out of the equation. That's it will not affect the rate, the change of the rate, because it stays the same. The only thing that's going to happen is B is going to double, and that would be the only thing that would affect the initial rate. Or for example, if you look from 1 to 3, it doubles in A, but B remains the same. So then B goes out of the equation right here, and you can say, oh yeah, A doubles, what happens to the rate from 1 to 3? So compare 2 experiments with one similar concentration. Now, how does it change? So if the rate doesn't change when you're doubling or changing the concentration, then the order or the exponent is 0. If the rate doubles while the concentration doubles, then it's first order. If the rate quadruples when you're only doubling the concentration, then it's second order. Now, if those don't make sense, then you do the math. When in doubt, do the math. I'll show you the math, but some people just like to think about it in their head, and I'll show you how to do that in this part right here. So let's do letter A right here, where we take this equation and find the rate law. We know it's going to be rate equals K, and then it's going to be A to some power, B to some power. What are those powers? Well, the first thing that we do is compare 2 experiments with one similar concentration. So experiment 1 and 2, A does not change. Take that out of the picture. B doubles. What happens to the rate from 1 to 2? Well, the rate does not change. Well, if this doubles and the rate doesn't change, it's 0th order. So that means B must be to the 0 power right here. That's the exponent. I'll show you the math in just a second for that. Let's do one for A. So A doubles from 1 to 3. B remains the same. So take B out of the equation now. And then if you look, A doubles. What happens to the rate? The rate goes from 4 to 16. See why you ignore those exponents there? You just look at 4 to 16, and now you can see that, oh, we doubled the concentration, we quadrupled the rate. Quadruple the rate means it's second power, so A would be to the second power right here. Now, if you're not sure about these, you can go ahead and do the math. So here's how the math works. When you're comparing these two, take the big concentration right here and put it on the top. So take 0.2 and put it over 0.1. 0.2 over 0.1 right here. Then take your rates. You know, these right here are going to have to be to some exponent, so raise those to some power. We'll call it n. And then take your rates and put them on top of each other. You can ignore the times 10 to the negative, but it would be 4 divided by 4, so 4 over 4. All right, 0.2 divided by 0.1 is 2, to the n is equal to 4 divided by 4 is 1, so 2 to the what power is equal to 1? Well, n has got to be equal to 0. That's where I got the 0 power right here. How did I do that? Well, let's do that again for this one. So now take the big one, put it over the little one. We're comparing 3 to 1. So 0.2 over 0.1. Raise that to some power. Let's call it m. And now that's going to have to equal 16 divided by 4, right? Because 16 divided by 4 right here. So 2 divided by 1 is 2. To the m is equal to 16 divided by 4 is 4. So that means m has got to be equal to 2. Oh, that's where the second order power came from right here. Second power. So that's my rate expression right here. Rate is equal to k, a to the second, b to the 0. And remember, that anything to the 0 power is 1. So you actually could write this rate expression as rate is equal to a squared. And just be done. Not write b in there, because anything to the 0 power, of course, is 1. All right, letter B. Find k with units. Ooh. All right. Take an experiment. It doesn't matter which one. Okay? Plunk those numbers into your rate expression. So, pick number 1. Rate is equal to 4 times 10 to the negative 5th molarity per second equals k. That's what we want to find. A is 0.1 molarity squared. Okay? 0.1 molarity squared. Solve for k. Divide both sides by 0.1 molarity squared. Divide this side by 0.1 molarity squared. So that means each of these are squared. Kind of goes into each one right there. Okay, these cancel with one another. And I'm going to pull it up in the book right here so that you can follow along if you want to as well. We have 4.5 times 10 to the negative 5th divided by 0.1 squared. You can see their math right here is the same as mine. And so then this would end up being k equaling 4 times 10 to the negative 3rd. And then watch my units right here. Notice how it's molarity over seconds over molarity squared. So when you have this type of thing, I'm going to write this over here on the side so you can see it a little bit better. Rewrite it like this, molarity per second. This is technically molarity per second over 1 because you can write any number over 1 and it's that. And then when you have complex fractions like this, they always say multiply by the inverse. So inverse this one and write it as 1 over molarity squared like that. All right. This one cancels, and what am I left with? 1 over seconds times molarity, or you could write it as seconds negative 1, molarity negative 1. So there is my rate constant with its units. And then letter C asked, what is the reaction rate if A is equal to and B is equal to? So now that we know K, we can plug K into this equation, and we're told A right here, and we're told B. Now B is not going to make any difference because it's obviously to the 0 power, but in case it would, we'd put that number in as well. And we want to find rate. So rate is equal to 4 times 10 to the negative 3rd, 1 over seconds times molarity. That's our K right here. And then A is 0.05 molar, and then square it right here. And then we could put B in there, but you know, it'd be 0.1 molar and it'd be to the 0 power, and anything to the 0 power, of course, is 1, so you're just multiplying by 1. So now multiply those guys together, and we end up with, if we want to zoom in on their work right here, 4 times 10 to the negative 3rd times 0.05 squared, we end up with the rate equaling 1 times 10 to the negative fifth. And the units here, this would be molarity squared, so one of these will cancel with this, and we'll end up with molarity per second, which is exactly what we want to see for rate, concentration per unit time. All right, that's one example. The next video will have a second example of doing the exact same thing.